Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Measurement of Resistivity from the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the various methods of measurement of resistivity are described. Four-probe method is explained and is illustrated for measurements on thin film. Also, in this module, 4-point measurement for resistivity calculation is carried out on a thick film with and without edge boundary conditions. Van der Pauw method to determine the resistivity of uniform samples is also described in detail in this module. Finally, two-probe method is discussed and is compared with the four-probe method. Let us begin with the four-probe method. The potential probe is most commonly employed method for measuring the resistivity of samples with low resistance value. Potential drop across two probes is measured and the gap between them, that is D, is taken as the sample length, and the gap between them is the D and sample length is taken as L. If the probes are notch point contacts, then the true value of probe distance is the gap between the centers and not the shortest distance between them. Figure displays the schematic demonstration of the experimental procedure. We know resistivity rho will become rho equals Vd into A divided by D into L. Four-probe method equally applies to single crystal or bulk samples and can determine their resistances. Current flows through outer contacts near the sample edges and the potential difference is gauged across the inner contacts. Hence, effect of interfacial resistance between electrodes and sample is eliminated by using this method. Thus, it is a precise technique for load resistance measurements. Though the contact and probe resistance themselves are cancelled out, there is still possibility of error in measurements if the contacts produce heat. Therefore, low resistance of contacts is preferable. The error due to DC offsets in the instrument is readily overcome by subtraction. Additionally, self-induced voltage offsets within circuits can increase the error. This may be rectified by flowing reverse current in the sample. A small voltage of the order of few microvolts might develop across the sample, thereby adding signal noise and increases the error. This error can be reduced by shielding the cables, single point grounding, etc. And the current density following conditions underneath the are required to satisfy for the resistivity measurement of a cylinder divided by 2 pi r square. First, the material possesses the current density uniform resistivity due to the current I measurement area. That is, second, injected into the minority carriers from R1 are injected and collected at R2 by placing the current conducting electrodes. Much of these carriers recombine at the electrodes. I12 divided by 2 pi negligible influence in the brackets vector R minus vector R1 the surface To
the
place
cube
the
of
probes
modulus
should
of
be
vector r
flat
minus
without
r1.
any surface leakage.
Fourth, the probes employed in measurement should touch the surface in straight line. Fifth, the diameter of contacts between the probes and semiconductor should be smaller than the gap between the probes. Finally, the material surface can be either conducting or non-conducting. The boundary is conducting when a material having lower resistivity is deposited. Non-conducting boundary results from plating the semiconductor surface insulator. The various applications of 4-pro measurement include: first, remote sensing areas; second, resistance thermometer; thirdly, it is highly useful in induction hardening processes. Also, it provides a precise estimation of geometrical factors. Moreover, 4-point measurement is very helpful for characterization of fuel cells' bipolar plates. A simple ohmmeter can be used to measure the resistance of the contacts, samples, and cables connected to the sample. In case of electrical contacts created with micromanipulators, the measurement of contact resistance becomes challenging due to the small contact area. The problem of the contact resistance can be overcome using a 4-probe configuration. In this method, the current flows through the outer 2 probes, while the voltage is measured across the inner probes, as can be seen in the figure. The current is injected in the sample through contact 1 and leaves the sample at contact 2. Rs represents the resistance of the sample, and Rm represents the equivalent resistance of the voltmeter. Vs represents the voltage across the sample, and Vm is the measured voltage. Let us next study the 4-point measurements on a thin film. As the current I is injected through the point contacts which are placed on the sample, which is a thin conducting film having a uniform resistivity ρ, the current spreads radially, and the current density around the contact is given by J is equal to I divided by 2 pi T R cap. The spreading of current is also shown in the figure. If 2 current contacts are placed on a thin film of thickness G and current I12 is injected at position R1 into the surface while extracted from position R2, then the currents are being added, producing following dipole pattern. The thin film approximation is valid only if the interspacing between the contacts is much larger than the film thickness. In such case, the current density can be expressed as J is equal to I12 divided by 2 pi t into, within the brackets, R vector minus R1 vector divided by vector R minus vector R1 modulus whole square minus vector R minus vector R2 divided by the square of modulus of vector R minus vector R2. Electric field can be obtained as the product of resistivity ρ and the current density as E is equal to ρ into J. This is equal to ρ into I12 divided by 2 pi t into, within the brackets, vector R minus vector R1 divided by square of modulus of vector R minus R1 minus vector R minus R2 divided by the square of modulus of vector R minus vector R2. The measured voltage across R3 and R4 can be obtained by integrating the electric field from R3 to R4. Thus, the potential measured at R4 with respect to the potential at R3 can be expressed as V43 is equal to minus rho I divided by 2 pi t into the integral going from R3 to R4 vector r minus vector r1 divided by square of modulus of vector r minus r1 minus vector r minus r2 divided by the square of modulus of vector r minus r2 into dr. Since measured voltage does not depend upon the path which is taken for its measurement, so we can integrate first in x direction and then in y direction, so that we have V43 to be equal to minus of rho into I12 divided by 2 pi t into the integral going from x3 to x4, integral going from x3 to x4 within the brackets in the integral sign x minus x1 divided by x minus x1 whole square plus y3 minus y1 whole square minus x minus x2 divided by x minus x2 whole square plus y3 minus y2 whole square brackets close dx minus rho times I12 by 2 pi t, the integral going from y3 to y4, y minus y1 divided by x4 minus x1 whole square plus y minus y1 whole square minus y minus y2 divided by x1 minus x2 whole square plus y minus y2 whole square dy. The voltage obtained after performing integration can be expressed as V43 is equal to rho times I12 divided by 4 pi t into L31 minus L32 minus L41 plus L42. Here Lmn is equal to natural log of xm minus xn whole square plus ym minus yn whole square. So resistivity can be obtained as rho is equal to 4 pi t into V43 divided by I12 into the inverse of L31 minus L32 minus L41 plus L42. When the thickness of conducting film is not known, the term R square, that is, the sheet resistance, is provided. Sheet resistance denotes the resistance of a square of the film. As can be seen in the diagram, the film has a length of L and a width of W and thickness is G. Then the R square is equal to rho L divided by W into T. This is equal to density rho divided by T, as because the film is a square. So this equals 4 pi into V43 divided by I12 into the inverse of L31 minus L32 minus L41 plus L42. We next discuss the 4-point method for thick film resistivity. A current I is injected through the contact which is placed on a flat surface of the sample. The sample is assumed to possess a uniform resistivity of rho. This current spreads radially and the current density underneath the contact may be expressed as J equals I divided by 2 pi r square into r cap. The current density due to the current I12, that is injected into the sample from R1 and collected at R2 by placing two current contacts on flat surface, can be expressed as J equals I12 divided by 2 pi into, within the brackets, vector R minus vector R1 divided by the cube of modulus of vector R minus R1 minus vector R minus vector R2 divided by the cube of modulus of vector R minus R2. Consequently, thick film approximation requires the distance between the contacts to be much shorter than the film thickness. The product of resistivity and the current density gives the electric field as E equals rho into J. This equals rho into I12 divided by 2 pi into within the brackets vector r minus vector r1 divided by the cube of modulus of vector r minus vector r1 minus vector r minus vector r2 divided by the cube of modulus of vector r minus vector r2. The potential at R4 with respect to R3 is V43 equals minus rho into I divided by 2 pi into the integral going from R3 to R4 vector r minus vector r1 divided by cube of modulus of vector r minus r1 minus vector r minus vector r2 divided by the cube of modulus of vector r minus vector r2 dot dr.
In the xy plane, the voltage can be found by integrating first in x and then in y direction as V43 is equal to minus rho into I12 divided by 2 pi multiplied by the integral going from x4 to x3 within the integral x minus x1 divided by x minus x1 whole square plus y3 minus y1 whole square, the denominator raised to power 3 by 2 minus x minus x2 divided by x minus x2 whole square plus y3 minus y2 whole square, the denominator raised to power 3 by 2 into dx minus rho into I12 divided by 2 pi into the integral going from y4 to y3, y minus y1 divided by x4 minus x1 whole square plus y minus y1 whole square, the denominator raised to power 3 by 2 minus y minus y2 divided by x4 minus x2 whole square plus y minus y2 whole square, denominator raised to power 3 by 2 into dy. The voltage which is obtained after performing integration can be expressed as V43 equals rho times I12 divided by 2 pi into within the brackets 1 by S41 plus 1 by S32 minus 1 by S31 minus 1 by S42. Here Smn is equal to square root of xm minus xn whole square plus ym minus yn whole square. Finally, the expression for the resistivity of a thick film is rho equals 2 pi into V43 divided by I12 into 1 divided by within the brackets 1 by S41 plus 1 by S32 minus 1 by S31 minus 1 by S42.
Let us next discuss the 4-point measurement for resistivity calculation on a thick film with edge boundary condition. A current I is injected through a current contact placed on a flat surface of the sample having a uniform resistivity rho. The current spreads radially along and the current density below the contact is given by J is equal to I divided by 2 pi r square into vector r cap. The current density due to the current I12 is given by vector J equals I12 divided by 2 pi into within the brackets vector r minus vector r1 divided by cube of modulus of vector r minus vector r1 minus vector r minus vector r2 divided by the cube of modulus of vector r minus vector r2. If the contacts are near the edges of the sample, boundary effects appear which need to be considered. This can be achieved by placing two image current sources near the edges of the sample. These additional current sources are mirror images of the real current sources, and the arrangement is shown in the figure below. The expression for current density changes to accommodate the additional current sources as vector J is equal to I12 divided by 2 pi into within the brackets position vector R minus position R1 vector R1 divided by cube of modulus of vector R minus vector R1 minus vector R minus vector R2 divided by the cube of modulus of vector R minus vector R2 plus vector R minus vector R3 divided by the cube of modulus of vector R minus vector R3 minus vector R minus vector R4 divided by cube of modulus of vector R minus R4. The electric field becomes E equals rho into J. This equals rho into I12 divided by 2 pi into within the brackets vector R minus vector R1 divided by the cube of vector R minus vector R1 minus vector R minus vector R2 divided by the cube of modulus of vector R minus vector R2 plus vector R minus vector R3 divided by the cube of modulus of vector R minus vector R3 minus vector R minus vector R4 divided by the cube of modulus of vector R minus vector R4. Similarly, the voltage between positions R5 and R6 on the surface can be obtained by integrating the electric field from R5 to R6. Thus, the potential at R6 with respect to the potential at R5 is V65 is equal to minus rho into I12 divided by 2 pi into the integral going from R5 to R6 within the brackets under the integral sign vector R minus vector R1 divided by the cube of modulus of vector R minus R1 minus vector R minus vector R2 divided by the cube of modulus of vector R minus vector R2 plus vector R minus vector R3 divided by cube of modulus of vector R minus vector R2 plus vector R minus vector R3 divided by the cube of modulus of vector R minus vector R3 minus vector R minus vector R4 divided by the cube of modulus of vector R minus R4 brackets close GR. In xy plane, the voltage can be calculated as V65 is equal to minus rho into I12 by 2 pi, the integral going from x5 to xx. Within the brackets under the integral sign, we have terms x minus x1 divided by x minus x1 square plus y5 minus y1 whole square. The entire term is raised to power 3 by 2 minus x minus x2 divided by x minus x2 whole square plus y5 minus y2 whole square, the entire term raised to power 3 by 2 plus x minus x3 divided by x minus x3 whole square plus y5 minus y3 whole square, the entire term raised in the denominator raised to power 3 by 2 minus x minus x4 divided by x minus x4 whole square plus y5 minus y4 whole square, the entire term raised to power 3 by 2 dx minus rho into I12 by 2 pi, the integral going from y5 to y6 under the integral sign within the brackets y minus y1 divided by x6 minus x1 whole square plus y minus y1 whole square, the term in the denominator raised to power 3 by 2 minus y minus y2 divided by x6 minus x2 whole square plus y minus y2 whole square, the term in the denominator raised to power 3 by 2 plus y minus y3 divided by x6 minus x3 whole square plus y minus y3 whole square, the entire term in the denominator raised to power 3 by 2 minus y minus y4 divided by x6 minus x4 whole square plus y minus y4 whole square, the entire term in the denominator raised to power 3 by 2 brackets close gy.
The resulting voltage from the above integral comes out to be V65 equals rho into I12 divided by 2 pi into within the brackets 1 divided by S61 plus 1 divided by S63 plus 1 divided by S52 plus 1 divided by S54 minus 1 divided by S51 minus 1 divided by S53 minus 1 divided by S62 minus 1 divided by S64. Here Smn is equal to square root of xm minus xn whole square plus ym minus yn whole square. Finally, the expression for resistivity can be written as rho equals minus 2 pi into V65 divided by I12 into 1 divided by within the brackets 1 by S61 plus 1 by X63 plus 1 by S52 plus 1 by S54 minus 1 by S51 minus 1 by S53 minus 1 by S62 minus 1 by S64.
Let us next discuss the two-probe method. Two-probe technique is suitable for measuring resistivity of high resistivity samples, example polymer films or sheets. As can be seen in the figure, the resistivity is calculated from the voltage drop V and the current I, which is rho is equal to V into A divided by I into L, where A is the cross-sectional area of the specimen as shown in the figure and L is the length of the specimen.
Let us now discuss the advantages of 4-probe method over 2-probe method. 4-point probe is preferred than 2-point probe as the contact and spreading resistances in 2-point probe are very large and the true resistivity cannot be actually separated from measured resistivity. In the 4-probe method, contact and spreading resistances are very low with voltage probes and hence accuracy in measurement is usually very high. To measure very low resistance values, 4-probe method is used. The resistance of probe will not be added to that of the sample being tested. It uses 2 wires to inject current in the resistance and the another 2 wires to measure the drop against the resistance. Coming on to van der Pauw method. The van der Pauw technique is employed to determine resistivity and Hall coefficient of a material. It can accurately measure the sample's properties having any shape if the sample is two-dimensional solid, that is without holes, and electrodes positioned and the electrodes are positioned on its parameter. It uses 4-point probes positioned around the parameter of the sample rather than in straight line. Therefore, this method measures the average resistivity of the sample while the linear arrangement measures resistivity only in the measuring direction. This difference is crucial to anisotropic materials which can be efficiently characterized by Montgomery method, which is an extension of van der Pauw method. Following properties of a material can be measured by this method. The first one is the resistivity. Secondly, we can find out the doping type in the material. That is, whether the material is P type or N type. Third, the sheet density of majority carriers per unit area can be determined using this method. Also, charge density and doping level can also be estimated using van der Pauw method. Van der Pauw method is a good method to study the mobility of majority charge carriers.
Let us now discuss the conditions where to apply the van der Pauw method. The following conditions must be met in order to apply the van der Pauw method. First, the sample must be flat-shaped and uniformly thick. Secondly, sample should not possess isolated holes. Third, sample should be isotropic and homogeneous. Fourth, the contacts should be placed at sample edges. Fifth, the contact area of individual contacts must be smaller than sample area, at least by an order of magnitude. We will now discuss the van der Pauw method to determine the resistivity of uniform sample. This technique was invented by van der Pauw and is extensively employed in semiconductor industry for determination of resistivity of uniform samples. This technique requires an arbitrarily shaped thin film sample having four very small ohmic contacts which are placed on the periphery, usually at the corners of the plate. Figure 4 shows the schematic arrangement of a typical van der Pauw experiment for determining the characteristic resistances Ra and Rb. What are Ra and Rb? To determine the resistivity of a uniform sample, the sheet resistance Rs needs to be determined. As demonstrated by van der Pauw, so two characteristic resistance Ra and Rb are associated with the corresponding terminals which are shown in the figure.
These characteristic resistances, that is Ra and Rb, are related to the sheet resistance Rs through the van der Pauw equation as exponential of minus pi into Ra by Rs plus exponential of minus pi into Rb by Rs is equal to 1. Let us call it as equation 1. Then the above equation can be solved to obtain Rs. Thus, the bulk resistivity, that is rho, can be obtained from Rs as rho equals Rs into D. This is equation 2. For determining Ra and Rb, a DC current, that is I, is applied across contact 1 and contact 2, and the voltage V43 is measured across contact 4 and contact 3, which is shown in the figure. Similarly, voltage V14 is measured across contacts 1 and 4. By applying a current I across the contacts 2 and 3. Ra and Rb can be obtained as follows. Ra equals V43 divided by I12 and Rb equals V14 divided by I23. Let us call it as equation 3. So students, let us summarize what we have learned in this module. In this module, the various methods of measurement of resistivity were described. Also, 4-probe method was explained and was illustrated for measurements on thin film. In this module, 4-point measurement for resistivity calculation was carried out on a thick film with and without edge boundary conditions. Also, 2-probe method was discussed and it was compared with the 4-probe method. Finally, van der Pauw method to determine the resistance of uniform sample was also described in detail. Thank you students for your attention.